common types of engineered materials. Composites, they are engineered materials. In composites, we have a matrix and a reinforced phase in it. The macro example of composite is that if you are putting a roof over a room, the cement and concrete, when you mix sand with cement, it makes a mixture called gravel, bajri. When you make blocks of that bajri, it has excellent compressional strength, but it doesn't have tensile strength. It breaks, it cracks, and you put steel rods in it. So the gravel phase, the concrete phase, is the metric phase, and the steel rods in it are the reinforcement portion. So you make composite which at least enhances one of the properties of the material. So the compressional strength was already there, and when you entered the steel rods, you gave it tensile strength. Tensile strength means that when I put pressure upon it, the steel rods will try to resist it. The concrete will break, but the steel rod will keep it in place. If I do the same thing at different levels, then we call them composites. The fiberglass, it is some fibers have been introduced. Glass is a brittle material, and when you put these fibers into it, you give it tensile strengths. The type, their arrangement of atoms, ions, and molecules gives that particular property to particular materials. Which type of atom is? What is its behavior? What are its intrinsic properties? Sugar is sweet, chili is hot. You should know among the atoms that which atom is hot and which atom is sweet. Which atom will give me more polarization? Which atom will give me more conductivity? Which atom will give me more strength to the material? What type of bond it will form? This is the understanding of materials. Metals are usually ductile, but ceramics are usually brittle. And again, if you go back to the atomic structure of those materials, which atom will prefer to form an ionic bond and which atom will prefer to form a metallic bond? Which atom will prefer to make a weak bond? Which atom will prefer to make a strong bond? A material scientist must know that if he or she is moving forward. So the metals are ductile because of that atomic structure, and ceramics are brittle because of that specific sort of bonding, as I told you. Then comes the polymers. They have poor tolerance to heat. Ceramic withstand very high temperatures. When we say withstand high temperature, what does it mean? They don't melt. When we say something withstand high temperature, which means that they don't melt at high temperatures. Why material is not melting at high temperature? As a physicist, can you tell me?
The bond is strong.
The bond is strong. Melting is nothing. It is the breaking of the bonds. If the bonds are weaker, the material will melt at low temperature. When the bond is stronger, it will withstand thousands of degrees. So as a physicist, you don't see that when a material melts, is subjected to high temperature, it melts. And if it doesn't melt, it will be ceramic. No, as a physicist, you look into the bond structure. This will guide you towards the properties of material. Metals are opaque while silicate glasses are transparent or translucent. Why? Because of its behavior towards light. Can something transmit light or not? Can something refract light or not? Can something reflect light or not? Again, a dense material will have a different behavior in comparison to a less dense material, rare material. So again, it is dependent upon the structure. Metal, good conductor of heat and electricity, and ceramics are poor. Again, because of the free electrons. Electrical conductivity of semiconductors increase with temperature, but that of metal decrease with temperature. This means that in physics and chemistry and related disciplines, you are thinking about a compromise between the potential and the kinetics. The potentials and the kinetics. Kinetically, you allow things to move within a material. Potential pulls them or repels them. Now you balance that potential and kinetics through processing. Processing includes grinding. Processes includes heating. Processing includes pressing and different environment. And you are making compromises between the kinetics and the potential of a material to make materials. For example, I had a material and it has this atom and it has this atom. And these two are tungsten atoms. For example, their bond is very strong, right? But if this much distance is between them, this means potential wants them to be together, but kinetically it is impossible to reach here. In kinetics, the kinetic energy is injected through heat. That is why you heat materials. You make the atoms and molecules mobile. You allow or give an opportunity to the mass transport inside the material. That wherever an atom wants, it goes there. But if an atom wants 100 times potentially, but kinetically it is not possible, it will not move. So, similarly, as I told you in the start, that if you make a material and freeze it, freeze means you cut the kinetic part, only potential can do nothing. It will be there unless and until you provide it enough temperature to get rid of that, right? So two things are governing these things. Ceramics are more resistant to harsh environments, while metals are not. You leave a spoon inside the room, if it is not stainless steel, it will be rusted in a few hours, in a couple of days. But a ceramic material living for thousands of years, they are still there, they are resistant to harsh environment. You see in prehistoric buildings, the ceramic bricks and different things. Biomaterial, compatible with the body of an organism. What is compatibility? Compatibility means that when you put a bone implant, it is not hazardous to your body. Secondly, it is liked by your body organs. Biocompatibility means that it is not hazardous and it is accepted by your body environment. So biomaterial comes in various forms: ceramics, metallic rods, smart material category, glass ceramics, and different things are made compatible with the body for various parts of the body. Similarly, nowadays people make veins and arteries from these materials, joints, and a lot of work is going on. And on the basis of that behavior, their reactivity, their properties, mechanical properties, people generally divide materials into metal, ceramics, and polymers. So these are various types of classifications, and we will move forward from here in the next lecture and about that. But the biomaterials were basically developed for implants. For example, for tooth implantation, you lose your natural teeth and you put the artificial teeth, so they are for implantation. Similarly, in bones and some parts of the other parts of the body, But drugs and all these things, they are inorganic materials in most cases, and their job is not to become part of the body. Their job is to treat a particular problem in your body. So they are not permanently there, but still effort is made by the pharmacists and chemical engineers to keep the hazardness of that chemical under control, so that when it enters your body, it is targeting the problem and it is not damaging your body. So biocompatibility to some extent is there. But if you talk of antibiotic, means you are killing life with antibiotics. Its job is there, but it must be all the medical protocols and different things are associated with these. So they are not for implants. The biomaterial came for specific implantations, and this will develop because of that. The chemicals and drugs are coming from a long time, and they have a different category.